Welcome to my channel. Today we're going to explore one of the most fascinating questions in artificial intelligence. Where exactly is knowledge stored in AI systems? When we train a neural network, teach a model to recognize images, or let an agent learn to play games, where does all that learning actually go? Think of it like asking where memories live in a brain. In AI, the answer involves numbers, lots and lots of carefully tuned numbers. We'll journey through different AI architectures, from basic neural networks to complex transformers and reinforcement learning agents, and discover that despite their differences, they all share a common secret about how they store what they've learned. So let's dive in and uncover the hidden memories of artificial intelligence. Let's start with the most fundamental neural network architecture. In a basic feed-forward neural network, knowledge is stored in the connection weights between neurons. Think of it like a library where every bookshelf represents a weight, and each shelf holds a specific piece of learned information. When data flows through the network, it passes from the input layer through hidden layers to the output. At every connection, the signal gets multiplied by a weight value, numbers like 0.73 or negative 0.42. These aren't random numbers. They're the result of training, carefully adjusted values that encode everything the network has learned. The key insight here is that knowledge isn't stored in any single weight. It's distributed across all of them together. Just like how a memory in your brain isn't in one neuron, but spread across many neural connections, an AI's knowledge is encoded in the pattern of all its weights working together. This distributed representation is what gives neural networks their power and their resilience. Now, let's understand how these weights actually learn. The answer is gradient descent. Imagine a mountainous landscape where the height represents how wrong the network's predictions are. This is called the loss landscape. Our goal is to find the lowest valley, where errors are minimized. During training, we take a ball, representing our current weights, and let it roll downhill. The gradient tells us the direction of steepest descent, literally pointing toward lower error. We then adjust each weight slightly in that direction. The learning rate controls how big each step is, typically a small value like 0.01 to ensure we don't overshoot the minimum. The weight update equation is beautifully simple. The new weight equals the old weight minus the learning rate times the gradient. This process repeats thousands or millions of times, with each weight getting nudged a tiny bit toward values that make better predictions. Learning, in its most fundamental form, is just adjusting numerical values to reduce errors. Every skill the network develops, every pattern it recognizes, is ultimately encoded in these adjusted weight values. When it comes to image understanding, convolutional neural networks store their knowledge in a special type of weight called kernels or filters. Think of each kernel as a specialized magnifying glass tuned to detect specific visual patterns. A typical kernel is a small grid of learned weights, maybe 3 by 3 pixels. As this kernel slides across an image, it performs a convolution operation, multiplying its weights against the image pixels and summing the results. Different kernels learn to detect different features. An edge detection kernel highlights boundaries between light and dark regions. A corner detector finds sharp angles. Texture detectors pick up repeating patterns. What's remarkable is that these kernels aren't hand-designed. The network learns optimal kernel weights through training, just like the connection weights in regular neural networks. The output of convolution is called a feature map, showing where in the image each feature was detected. This is how CNNs store visual knowledge, in the precise numerical values of their kernel weights, each one trained to recognize specific visual patterns. One of the most elegant aspects of CNNs is how they build up hierarchical understanding. It's like building with Lego blocks, where simple pieces combine to create complex structures. In the first layer, kernels learn to detect the most basic features, edges, gradients, and simple lines. These are the fundamental building blocks of visual information. In the second layer, things get more interesting. The network combines those simple edges into shapes like curves, corners, and ovals. Notice how these are more complex but still abstract. By the third layer, the network starts recognizing meaningful parts: eyes, noses, mouths, wheels, windows. Now we're seeing combinations of shapes that represent real-world object components. Finally, in the deepest layers, these parts combine into complete object recognition. The network can now identify a human face by recognizing the combination of eyes, nose, and mouth in the right spatial arrangement. Each layer stores increasingly abstract features in its kernel weights. Early layers hold low-level pattern detectors, while deeper layers encode high-level semantic concepts. This hierarchical knowledge storage is key to how CNNs achieve human-like visual understanding.
Transformers, the architecture behind modern language models, store knowledge in a fundamentally different way, through attention patterns. Consider the sentence, "The dog chased the cat, it was fast." When processing the word it, the model needs to figure out what it refers to. Does it mean the dog or the cat? This is where attention comes in. The transformer learns attention weights that create connections between words. When focused on the word it, the attention mechanism creates connections to every other word, but with different strengths. The connection to dog is strong because the model learned that fast typically describes the chaser, not the thing being chased. Meanwhile, connections to other words are weaker. Think of attention like dynamic spotlights that illuminate relevant connections based on context. These aren't fixed rules programmed by humans. They're learned weight values that encode relationships between words. The attention weights themselves are the stored knowledge, representing which words should influence which other words during processing. This is how transformers understand context, resolve ambiguity, and generate coherent language.
Transformers don't just use attention weights. They also store semantic knowledge in embedding spaces. An embedding is a high-dimensional vector that represents a word or concept. Imagine a vast star map where each word is a point in space, and the distance between points reflect semantic similarity. In this space, similar concepts cluster together naturally. Words like king, queen, and prince form a tight cluster because they share royal semantics. Similarly, dog, cat, and puppy group together as animal concepts. What makes embeddings truly magical is that they enable vector arithmetic. Take the vector for king, subtract the vector for man, add the vector for woman, and you get a result very close to queen. The embedding space has captured the relationship that king is to man as queen is to woman. This isn't programmed explicitly, it emerges from training on massive text data. The positions of words in this high-dimensional space, the precise numerical values of each embedding vector, encode rich semantic relationships. These learned embeddings are fundamental to how transformers understand meaning and generate contextually appropriate language.
Modern large language models store knowledge in billions, sometimes trillions of parameters. Let's put this in perspective. GPT-2, released in 2019, had about 1.5 billion parameters. GPT-3 jumped to 175 billion parameters, over 100 times larger. GPT-4 is estimated to have around 1.8 trillion parameters, another order of magnitude increase. Each parameter is a learned weight value that encodes some piece of knowledge. When we talk about where knowledge is stored in an LLM, the answer is distributed across all these parameters, in the attention layers with their query, key, and value weights, in the feed-forward networks with their dense transformation weights, in the layer normalization parameters, and in the token embedding weights. Think of it as an enormous warehouse with billions of tiny storage units, each holding a fragment of learned knowledge. No single parameter knows a complete fact. Instead, knowledge emerges from the collective values of millions of parameters working together. This is why larger models tend to know more. They have more storage capacity for encoding the patterns and relationships found in their training data. Now let's shift to reinforcement learning, where knowledge is stored in a fundamentally different structure, policies. A policy is a mapping from states to actions, telling the agent what to do in any given situation. Consider a simple grid world where an agent needs to navigate to a goal. The policy tells the agent, when in position 0, move right. When in position 1, also move right. When near the goal, move down. This policy can be represented as a table, often called a policy table, where each row maps a state to the best action with some probability distribution. A policy that always takes the best action is called deterministic, while one that samples from probabilities is stochastic. Think of a policy like a refined decision tree that's been shaped by experience. Initially, an agent might have a random policy, taking arbitrary actions. Through trial and error, collecting rewards and penalties, the policy evolves to favor actions that lead to better outcomes. The policy itself is the learned knowledge, a complete strategy for behavior encoded in the state-to-action mappings.
Q-learning offers another approach to storing knowledge in reinforcement learning: Q-values. A Q-value represents the expected future reward for taking a particular action in a particular state. It answers the question, how good is it to do action A when in state S? The classic Q table stores these values in a grid where rows are states and columns are actions. High Q values, shown in green, indicate good state-action pairs that lead toward rewards. Low Q values, shown in red, indicate poor choices. The goal state naturally has the highest value of 1.0, while positions far from the goal or near obstacles have lower values. The Bellman equation governs how Q values are updated during learning. Each time the agent takes an action and observes a reward, it updates the corresponding Q value based on the immediate reward plus the discounted maximum Q value of the next state. Over time, Q values propagate backward from the goal, like waves spreading outward. Think of Q values as a treasure map that shows how valuable each action is from every position. The agent simply follows the highest Q values to reach the treasure. All the knowledge about navigation is encoded in these numerical values.
Deep reinforcement learning combines the best of both worlds, neural networks and reinforcement learning. Instead of storing policies or Q values in tables, we store them in neural network weights. A policy network takes a state as input and outputs action probabilities. The network's weights encode the policy, mapping potentially millions of different states to optimal actions. This is impossible with tables, but natural for neural networks because they can generalize to states they've never seen before. Famous examples demonstrate the power of this approach. Deep Q networks, or DQN, learn to play Atari games with superhuman performance, storing Q values in convolutional neural network weights. AlphaGo combined policy networks and value networks to master the game of Go, encoding millions of board positions in its weights. AlphaZero took this further, learning chess, shogi, and Go entirely through self-play, with all strategic knowledge residing in neural weights. Robot control systems use neural policies to learn complex motor skills. DeepRL merges the neural library with the decision map, enabling AI systems to learn sophisticated behaviors that would be impossible to engineer by hand.
Let's bring it all together. We've explored 4 major AI paradigms and discovered a universal answer to where knowledge is stored. In traditional neural networks, knowledge lives in connection weights and bias terms. In convolutional neural networks, knowledge is encoded in kernel weights and feature filters. In transformers, knowledge resides in attention weights and embedding vectors. In reinforcement learning, knowledge is stored in policy weights and Q values. Despite their different architectures and applications, every AI system shares the same fundamental secret: knowledge equals numbers that encode patterns. Learning is the process of adjusting these numerical values to better capture the structure of the data or the rewards of the environment. There's no magical memory bank or symbolic database, just carefully tuned numerical parameters that together create intelligent behavior. This insight connects all of AI, from the simplest perceptron to the most advanced large language models. They're all doing the same thing at the core, storing learned patterns in numbers. If you found this video helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.